project. So let me give a very short overview. It is, as you said, about the formation and early evolution of stars. And on the left-hand side, I show an embedded protostar class 1 system, as we call it. The very left side, the bottom of the screen, is an infrared image combined with an optical image of a protostellar jet from Hubble. And the overview of my talk will be, I will give initially a short introduction about the taxonomies and classifications, because NEMESIS is a lot about classifications of young stellar objects. And then I will discuss a little bit about the evolution of the field in terms of the evolution of infrared facilities and how the co-evolution, the infrared facilities we use, especially from space, they helped us study and understand the young stellar objects. I will move on to talk about the current classifications and how we understand today's star formation. And I will then move on why NEMESIS is relevant and what we're trying to do with NEMESIS. And a very important aspect of NEMESIS, which is machine learning, bringing machine learning techniques into astrophysics and star formation studies. I will give a short introduction, just a few slides on supervised and unsupervised techniques and how we plan to use these techniques in star formation studies. And then I will close my talk giving a few hints of the importance of NEMESIS for space science research in Austria. So let me start a little bit with taxonomies and classifications. And of course, they have played a very important role in the evolution of sciences. So we first collect and identify objects, and we put them in some sort of order. And after ordering observations of the natural world around us, then by studying them, then we can find the relations between them and make a development of how they may develop, or how they may evolve. And here I have a page from Carl Linnaeus, the Systema Naturae, which is the starting, if you want it, and then followed by the evolution with Gregor Mendel, an Austrian, of what is today known as modern day genetics about plants. And there is, of course, similar studies and efforts taken a few years later about animals, classifications of animals and taxonomies into different species. And there is no doubt that this image that I showed you is from Charles Darwin. And Darwin is the person, of course, the very well-known scientist who developed the theory for the evolution of the species. And this, of course, is no exception in astrophysics, in astronomy. We started very early on, at about the same time, with the early taxonomies of the physical world around us on Earth, to make catalogs of objects, starting, for example, with a general catalog of nebulae and clusters of stars with Herschel. This was developed eventually in the 19th century to the new general catalog by Dreyer. And we carry until today these names, these designations in the objects we study in the sky, the new general, the NGC acronym. And of course, this includes very diverse objects, and that's a problem we often face in modern day astrophysics, that these very old classifications and catalogs, they could not have the whole information. The resolution back then of the telescopes was such that you could not really distinguish between a fuzzy object that was a galaxy or a planetary nebula. So you had these objects being in just one single catalog, because back then it was not possible to distinguish the nature between these objects. And of course, we have more classifications. A very known and very important one for extragalactic astrophysics is the classification of what is called now the Hubble fork, the tuning fork from Hubble, the classification of different categories of galaxies, the elliptical galaxies, the barred galaxies, and the spiral galaxies. And if we move on from morphological classifications, once we started getting spectra from different sources on the sky, we started trying actually to classify their objects depending on their spectral features. And on the right-hand side, I have an example from very early spectra in the 19th century by an Italian astronomer, Secchi, who pioneered spectral classification, stellar classification. But what this was concluded at the beginning of the 20th century by a group of women, actually, who worked intensively in classifying stellar spectra. They're now known the Harvard computers. And it is based on their work that we managed actually to have the stellar classification we have today. And this classification is, again, awkward in the sense that it has scattered a random series of letters of the alphabet. And of course, no reasonable person would do such a classification. The thing is that the initial classification had to be reshuffled when we understood what are the properties of the stars and how the spectral features relate to the evolution of stars. And this is a pattern so that we have in astrophysics, in modern day astrophysics. It's a rather conservative science in the sense that when a classification is introduced, then we prefer to shuffle things rather than to rename them from the beginning. Let me mention that classification of stars is extremely important. It's actually the foundations of modern day astrophysics. It's extremely important. So let me go a little bit now to star formation and why star formation is important. And this is for many different reasons. The most basic one is that because it connects very different scales. So when we observe galaxies, the galaxies evolved by cycling the material, by transforming the material, the gaseous material of their content, for example, in the spiral galaxies, into stars, and then into dust, and so on and so forth. And this is actually shown by this relation, the Schmidt-Kennicut law. So the evolution of galaxies is to a great extent determined by the formation of stars and them and the cycling of the material. But this is also very important in terms of what kind of stars we make, because as most of you know, different masses of stars, they have very different evolutionary tracks and very different lifetimes. And in these respects, star formation or the end process of star formation has to do with the stellar masses that we have in the stellar content in a certain galaxy, in a certain system. And as we have now new facilities that we can observe planets around different stars, star formation is extremely important because the conditions for forming these planets and the conditions that that these planets may be habitable in the future depends really on how these systems form. And to bring it to our own solar system, this of course relates to the formation of Earth, of the solar system, and the first solids that we can now study in meteoritic samples, as the one I showed on the lower right-hand side of the slide. So star formation is a field that really brings together all different scales, starting from the evolution of galaxies to galactic star formation and to the planets, and of course the formation and evolution of our own solar system. Star formation is a rather new field, and it has to do a lot with, as I mentioned in my introduction, it goes hand by hand with infrared astrophysics, and this is mainly for two reasons. The first reason is that stars form in molecular clouds, and molecular clouds in the visible wavelengths, they're dark, they're opaque. So stars form in these regions that I saw in this famous star forming region. They form where the screen appears to be completely dark, or opaque. And that's the first problem. The second issue that we have is that young stars are very cold. So if we take them to first approximation to be black bodies, then they have temperatures of about, say, 70 Kelvin or a little bit higher. So this would be somewhere to the right-hand side of these curves, of these different black body curves, meaning that the maximum of their emission is in the infrared and actually the far infrared wavelengths. So the development of these facilities actually allowed us to study stars. First of all, penetrate in the molecular clouds, because dust becomes opaque at longer wavelengths. And then allowed us also to study their objects individually because these are very cold objects. Let me give an example. We have a camera, and many of you may have seen it. Franz Kirschbaum has it at the Institute of Astrophysics for demonstrations. That's a thermal camera. And what you see, the left-hand side is, of course, a normal photo. The right-hand side is the image from a thermal camera taking infrared radiation, what we call the thermal infrared. And by comparing the two, you can see lots of differences. The first one being that the thermal infrared can give you a mapping of the different temperatures. So the warmer parts of the body of this person, for example, on the head or the neck, they appear brighter, and the parts that they're covered with clothes, they appear cooler. Another very important feature is that the bag that he holds in his hand in the thermal infrared becomes opaque, so it becomes transparent, so you can see actually his hand. And if you really go into details, you may observe that his glasses, which are transparent in the visual wavelengths, they're actually opaque in the infrared. So infrared wavelengths, they can actually give a very different view. They can even penetrate through different obstacles and observe things that are much cooler. What is actually very important to also notice is that on the left-hand side, what you observe, how the photo is made, is with a flash, so it's a reflected light, and then the right-hand side is actually the body itself emitting the radiation. So that's why it's called thermal infrared. And of course, these sort of techniques, these sort of cameras in the infrared, they find lots of applications, like the night cameras that we're using today for many different purposes, right? Because thermal infrared, you can actually observe things directly. They emit radiation in the infrared. Going to the dust extinction, I try to avoid putting lots of plots, but I believe for an audience which is quite trained in basic astrophysics and has a good experience in instrumentation, this wouldn't harm a lot. I have an extinction curve for different opacities. On the right-hand side, you should read these plots with increasing wavelength from the right-hand side to the left-hand side. So smaller wavelengths are on the right-hand side, and you can see the scale on the top part of the plot. And what you see is that for different bands, for different filters, as we go from the visual wavelengths to the infrared wavelengths to the HK-LMN bands in the mid-infrared, actually the opacity, dust opacity drops very fast. And this allows us actually to see objects through molecular clouds, through the veiling of the dust from molecular clouds in a similar fashion as we saw in the previous figure, that we can see the emitting hand behind the plastic bag in the previous picture. So if we have opacities, for example, of the extinctions of about 25 visual magnitudes in the visual wavelengths, this would be, to quantify it a little bit, in the K band at the 2.2 micron, it would be an attenuation of the radiation by a factor of 10. And if you go to the M or the N bands, this would be just a factor of 2 to 4. So this means that we can go to deeper and deeper parts of the molecular clouds and see further through these objects. And there is no better way to demonstrate that with images. So the left-hand side image, that's a Bock globule, that's an isolated small cloud, it's just sitting in the middle of the Milky Way, of our galaxy. The left-hand side is a color composite image of the blue, the visual, and the infrared bands. And if you just change one filter and you make a color composite image of the blue, the infrared, and the K band, which is mid-infrared, 2.2 micron, you can immediately see the difference from an opaque object to an object that you can see the background stars as red dots. Even more, going to the infrared wavelengths is extremely interesting because at different wavelengths, we start observing different things. This is exactly the same object, the Bock globule 68, it's a famous object. And from the top left panel to the bottom right panel, I scanned through different wavelengths. So starting from a red filter, ground-based observations, and going to space observations in the mid-infrared, 3.6, 8 micron, 12 micron, and 24 micron. You see that the Bok globule, the dust opacity becomes becomes transparent, excuse me. And at about 100 micron, as you continue, you start actually what seems to be an absorber to start emitting itself. So this is the dust in this object has also a temperature, a very low temperature of maybe 30 Kelvin, and at about 100 micron, we start observing the emission of these dust particles. So instead of having something which absorbs radiation, actually we observe its emission, and this allows us, that's extremely important because this allows us to study. As we go to longer and longer wavelengths, the shape actually is changing. At the same time, I would like to draw your attention to the lower left corner. You see what is the resolution of the instrument, that's the beam size. And as we go to longer and longer wavelengths, of course, this resolution or the pixel size of changes. We have worse and worse resolution. This has to do, of course, with the telescope diameter, the dish, if it is for radio telescopes. But the largest dishes for single dish instruments we can build today is about 15 meters. So as the wavelength goes to, as we go to longer and longer wavelengths, it's unavoidable that the resolution will just get worse. We can overcome this difficulty today with interferometers. That's a rather new technique, and it's extremely important. I will come back to this in a few slides later. So let me show you one more image that actually shows this difference. That's an object that's it's very easily accessible with the eye from the northern hemisphere and part of the southern hemisphere. That's the Orion Nebula, and you can see directly with the naked eye even the Orion, the emitting region, the star-forming region at the Orion belt, below the Orion belt. If you see Orion with the Herschel Space Observatory at the far infrared at 100 micron radiation, it is completely different. What you observe is now the dust which radiates. And these two images, all the stars you see, or most of the stars that you see on the left-hand side, these are stars which are foreground stars. They're in front of Orion. As Orion is a quite dense molecular cloud, you cannot see stars behind Orion. Orion is at about 500 parsecs, so there are quite lots of foreground stars. And by observing on the right-hand side the distribution of dust, we can actually penetrate through, and we can see these clumps, which are locations where stars are forming. So I have already showed a few images, and I'm talking already about space observations, infrared space observations. And that's extremely important because without these observatories, space observatories, we couldn't have advanced significantly in the studies of star formation. The main reason for that is that much of the radiation from these very cold objects actually is it's around 100 micron. This is where the radiation peaks. And these are regions which are completely inaccessible from the ground. So we can only access these wavelengths from space. Near infrared, we can access there a few windows between, say, 1 micron and 20 microns, and then close to millimeter wavelengths or sub-millimeter wavelengths from very high locations. For example, the Atacama Desert in Chile, where it's ALMA today, we can take advantage of specific windows or atmospheric windows from the atmosphere of the Earth, and we can pierce through and can take observations. But for about wavelengths from, say, 20 micron to 300 micron, the only way to access these wavelengths is from space. And that's why space observatories have been extremely important in the evolution of the field. The first and most important mission we had in space is the satellite IRAS, infrared astronomical satellite. it was a modest telescope that we sent to space. It was helium cooled. As most of you know, since you start observing in the infrared, everything that has a temperature, it's a black body, so it radiates. So by cooling it down, you can suppress the thermal noise from the instrument itself, so you can observe the radiation coming from these very cold objects in the space. It observed in 4 bands in the mid and far infrared wavelengths, and it did an all-sky survey that lasted only for 10 months. So this moderate mission added about 350,000 new sources. It was, I would dare to say, a revolution for astrophysics. And it changed completely our understanding in the sense that so many objects were not seen from the ground, and actually signified that many of the objects, if not most of the objects in our galaxy, but also in space, in cosmos in general, they're infrared sources rather than emitting their major part in the optical or other wavelengths. For example, the stellar mass function in our galaxy, it's predominantly in lower masses, and these, for example, brown dwarfs or other cold objects, they predominantly emit in the infrared wavelengths. It is, of course, all the stars and the forming stars which are embedded into very dusty cocoons, and they're very cold objects. And there is no need to mention, of course, extragalactic objects, galaxies which are redshifted. So redshifted means that the major part of their radiation from optical wavelengths is shifted to the infrared. So with the advent, after the advent of this mission, the completion of this mission, a few years later, there is the first classification coming, published about young stellar objects from Lada, from again, Harvard. Harvard has played a very important role in modern day astrophysics. And it follows this scheme, actually takes advantage of the basic characteristics. I will explain that in a bit more detail. They proposed 3 classes for young stellar objects. One that describes a source which is embedded, as we say, or surrounded by a cocoon of very dense material, which is cold material. So you cannot directly observe the forming star, but you can observe just a very cold envelope around it. And then after some time, this envelope is dissipated either by forming the star or by just blown away by, as we will see, protostellar jets and outflows. And what you're left with is a forming star, which is now fed by an accretion disk, which is called protoplanetary disk, because this is the location we expect planets to form. And then there is a third class, what we call the class 3. This is now the accretion and the formation of the central source is completed. What you're left with is a debris disk. It's a leftover disk where after a long time, as the theory of the day was, through collisions, the dust coagulates in the larger and larger bodies, and then the formation of planet occurs. So let me explain a little bit how we do classify these objects. And I just draw a sketch here. So a sketch of a black body, of a very cold black body, which would be an embedded protostar without any extra features like the envelopes or the disks. And as the envelope is being consumed around these very cold objects, then you would have something, you will start seeing a warmer object, which is it's a star that starts being seen through this envelope. So it's something warmer. And then as the envelope is completely dissipated or more dissipated, then you can see a warm protostar, which is just, it is about to start to be ignited and start consuming its hydrogen, so moving to the main sequence. So the idea for this classification is very simple. You can define a very special region, which is in the near mid-infrared, this shaded area. And over the shaded area, you just need to take the slope of this region. So for the very cold objects, the class 1 objects, this slope is positive. And then as you move to the class 2 object, this slope becomes negative, and even more negative for the class 3. And this is a very smart and a very efficient way to make a very first classification for young stellar objects. Well, after a few years, we started developing techniques for observing what we call sub-millimeter wavelengths. These are special techniques. Actually, it has to do more with the detectors rather than with the telescopes. The telescopes look very much like radio telescopes, but the detectors are very special and technically very hard to develop. So they were developed, and they still keep on developing. But the first developments were at the beginning of the 90s. And when this instrumentation was developed, then we have the introduction of yet a younger class of objects, which are now coined the class 0 objects. And this, of course, brings a new class and a new series, creates the same problem as we had, for example, with the classification of stars at the beginning of the 20th century. As we now have a sequence for the evolution of young stellar objects following a class 0, which is an Arabic numeral, followed by a class 2 and 3, which are Latin numerals. And as you very well know, Latin numerals do not have a 0. So the 0 comes as an inconsistent description, unfortunately, for these this idealized picture of how stars evolve. So class 0 objects are they're very cold objects surrounded by very dense envelope. As this envelope contracts, at the center you have the protostar forming. To remove angular momentum, we believe, and we actually observe that there are always protostellar jets and outflows being ejected by the systems. Actually, in the past, especially, and before the advancement of far infrared and sub-millimeter techniques, it was easier to detect the jets and the outflows, and then by backtracing their motions to figure out where the embedded protostars were laying. This is now followed to this scheme by the class 1 stage, where you start consuming much of the envelope material. You start seeing more structures, internal structures of the protostar, possibly part of the accretion disk. And of course, the envelope material is also ejected outwards or consumed by these widening, what we call wider outflows. So these cavities that they push material outwards. And eventually the surrounding material of the envelope is almost completely consumed, and we reach the class 2 phase. And when the disk material is also consumed, and what remains from the disk is mostly dust, then that's the class 3 phase, or the weak line Titori phase, as we call it. And this is according to the standard star formation and planet formation scenario, when planets, after a few million years, start forming. In terms of SEDs and putting things into context, you start with a very cold black body, which emits mainly in the far infrared, and then this object they shift in this idealized plot to the emission shifts as you consume the envelope to the near infrared, and then even to the visual wavelengths, the optical wavelengths. For example, the class 2 and the class 3 objects, we can directly observe the central object. And by observing the central object in these classes, we can deduce ages, we can model them and deduce ages for them. And then we go to molecular clouds and we do number statistics. So we do number statistics of how many class 3, class 2, class 1, and class 0 objects we have. And by knowing the ages of the class 2 and the class 3 that we can deduce, then we can extrapolate the ages for the class 1 and the class 0 phases. And the reason for that is because we cannot observe the central object in these classes, so we cannot possibly model their evolution. So ages for these sources, they depend a lot on how we classify them. And if we don't classify them properly, then the revolutionary, how fast they evolve may change just because of the number statistics we were using to deduce their ages. And in fact, this very simple classification that we're using still today is prone to large uncertainties. And the reason for that is that behind this idealized view, what is happening, excuse me, what is happening is that if you observe these objects at different inclinations, they can actually mimic a different class. So a class 0 phase, when it is seen at an inclination that allows you to peep through a little bit through these outflow cavity walls, then you can see a little bit of the central source, then it's going to appear as a warmer object. So it can mimic a class 1 object. Or for example, if you see a class 2 object, edge-on, so you have the disk, a thicker disk covering the central object, this can mimic a slope or an SCD distribution, which is more, again, like a class 1 object. So just if you play with the inclination, and of course, on the plane of the sky, all these objects are randomly inclined to us, then you can misclassify them rather easily. And when you misclassify them, we do the number statistics in a wrong way. And of course, the ages we deduce for the revolution, they're not accurate enough. And this can lead to surprises. So when we try to put these objects in evolutionary diagrams, so this would be plots that they are almost equivalent in a sense in terms of physical units to color magnitude diagrams or Hertz-Russell diagrams that you would see as you see the evolutions of stars. Then what we observe is that our classification produces a very large scatter. So we don't see an accurate or a well-defined evolutionary pattern between them. So our classification seems to have problems in describing how the sources are forming and how fast they develop. So what has changed ever since the first classifications? The whole classification scenario, it was really fossilized until the beginning of the 90s, until 1994. What has changed since then? Well, we have many more space missions. We have the top left corner Akarian WISE missions. These were small missions, but all sky surveys similar to what IRAS did. But we had also a series of large infrared telescopes that they did pointed observations, like the Infrared Space Observatory, Spitzer Space Telescope, and the Herschel Space Observatory. That has been the largest mirror, actually, that we carried ever to space for those wavelengths. And we're going to have soon James Webb Space Telescope. This is the successor, as it is going to Hubble, but actually that's an infrared telescope. It's not a visual telescope and visual wavelengths like Hubble. And on the other hand, we have developed interferometric arrays. So in the sub-millimeter or millimeter wavelengths, where we observe the other part of the SCD at the of these cold objects, we have developed these arrays, and these arrays, they're interferometers. By combining the signals from these telescopes, we can actually, when we have the antennas at different separations, we can actually have much higher resolutions. And from the very first arrays, like the Caltech sub-millimeter observatory that was in Mauna Kea, we now have two large arrays. One is NOIMA, is in France, the northern hemisphere, and the other one that most of you all know is the ALMA array, which is at the in Chile at the Southern Observatory. And these arrays actually, and all this instrumentation, they have allowed us to get a different view of how star formation is happening. So let me show you some interesting sequences. So this is again the star forming region I demonstrated before. That's the visual wavelength image, color composite image of a star forming region in Perseus. That's NGC 1333, is very well studied. Once we go, and this is a sequence of images in the infrared from space missions mostly. As we go to the mid-infrared with Spitzer, we immediately see a completely different view. All the dust extinction is gone away, or most of it, and we see many objects that are forming. These are forming stars. The green snake-like features or tails that you see, these are protostellar jets and outflows. This is hydrogen emission that we can observe in these objects. And then when we combine wavelengths, other filters, which are in the far infrared, this is again Spitzer and Herschel color composite images, we see the cooler objects. These are the very, very young stars. And as you can see immediately, even with bare eye, they have different colors. So we believe that the bluer and the redder sources, they correspond to different evolutionary stages within the same cloud. So these colors, the far infrared colors, actually, they may provide a much better descriptors for the evolution of those objects. If we go to even longer wavelengths.
May I just say maximum 7 minutes, please?
Yes, I'm coming to an end. So further longer wavelengths, we start observing the dust features and the colder envelopes of these objects. And then these wavelengths we start also getting from the ground. And with interferometers, we can zoom in and we can see that these clamps, which are not resolved from space observatories, they have structures within them. Let me go very fast to what is coming also with ALMA. ALMA starts resolving, these are class 2 objects, and these are the locations, these concentric rings, protoplanetary disks, and these rings are actually locations that we believe planets are forming. These are class 2 objects. Class 2 objects means they're a few million years old according to the standard classification scheme. And most of these objects, they seem to have already planets forming in these disks. Until we observe this system, which is just 1 million years old, again with ALMA, and this actually challenges our understanding about how well we're doing our classification and how well we derive the ages of how fast these systems form. This actually means that that's already developed a planetary system just 1 million years old. This corresponds to a class 1 object, which means that everything was even actually done before that, probably in the class 0 phase. So that's very, very early on. So what is NEMESIS all about then in this context? Well, the basic idea of NEMESIS is, for the first time after 25 years that this classification scheme was fossilized, to review and try to understand whether we can say, whether we can do better. So what we aim is to combine all this rich information we have from space missions and ground-based missions into the largest coherent and panchromatic data set of all nearby star-forming regions. By combining this information, then we would like to analyze it in an unbiased way. So in a way that we try to remove our individual biases of how these objects may evolve. And to this end, we plan to use machine learning techniques. And what machine learning is all about? Well, you know already, but it is a little bit if you've been using social media. And you have, when you upload images, pictures of you or your friends in social media, you may remember a few years ago, we were asked by the system, by the social media platform, oh, would you like to tag your friends? And then some of us would just type in a name into this tag and we say, yes, this is Maria, my friend. And we did that a few times for our pictures. The system was already smart enough not to ask for names of dogs, for example. It could already recognize faces. But after a point, if you notice, the question was not anymore tag your friend, if you would like to tag your friend, rather that if you would like to tag John. So the system already knew after a few times that you have said, oh, this is John, that for every new picture, even though John may wear now sunglasses or whatever other pictures or conditions that the picture was uploaded had, the system was smart enough to extract the information and tell you that this is John. And that's a unique thing, a unique power that machine learning techniques can bring. And we would like to use such techniques to actually extract the information from these data sets to characterize and classify our sources in a similar way. Machine learning for morphological classification is extremely powerful. but we don't want to stay to that. We would like to use unsupervised techniques. In these techniques, you just have a sample of objects and you let the machine do the job for you. Just the machine, okay, find me similarities and group them according to what you think is similar. So you may get groups of ducks, for example, in these cartoon heroes, or they may be classified just because they have yellow legs, yellow feet, or they may be just classified together because they have into groups that they have a hand extended versus hand not extended, or they may be classified as figures that they wear shoes versus figures that they wear no shoes. So you can understand that that's just for 5 heroes and five figures, and I just made a few a game of what similarities, how many different ways you have to classify them. Just imagine if you use data for a few thousands of sources with a few hundreds of data points in different characteristics and features each. That's a huge data space. And machine learning techniques and unsupervised techniques is the only way actually that you can examine in a coherent way this huge data set we plan to put together and extract new information of how these objects may be classified together in new ways that we could not even perceive or visualize with our eyes before. So who we are, really quickly, as I'm running out of time. NEMESIS is a generously funded Horizon 2020 project. This is a European project where 3 institutes, we're the leading institute in Vienna. I have a postdoc, Tatiana Pavlidou, who has started already with me, and a PhD student that will start soon. And it was done together with my colleagues, Marco Dart and Gabor Martin from the University of Geneva and the Hungarian Academy of Sciences. This is a family photo we have before the pandemic broke out. Exactly in February 2020, we met in Vienna to write a proposal. We have additional funding also from local resources, from FFG, from smaller projects. And we have also an extended network of collaborators, as for example, an EASY team that we bring together specialists, for example, from extragalactic astrophysics and computer specialists that they can help us to optimize what we want to do in terms of machine learning techniques. A last comment of why is this important for Austria and especially the space programs in Austria. As you may notice in these plots, Austria has been getting quite lots of funding. For example, it has Austrian projects are quite successful as a total share in the European Union. However, they don't manage to bring lots of money in, and they don't lead the projects as we do. So NEMESIS is one of the very rare projects that actually brings quite lots of money to Austria and we're the project leaders here in Vienna. And that's important also for the University of Vienna, as this is one of the only 2 projects, space projects, that the University of Vienna has ever taken. And actually, I've been participating also in the previous project that is the second project before NEMESIS. So with that, I would like to thank you for your attention and take your questions by giving you our last page. If you want to learn about us, I believe we're soon going to have very interesting results. Please follow us on our website, nemesis.univ.ac.at. And thank you very much.
Okay, thank you very much for that great talk. Fragen?
We have no questions from the chat room.
Okay.
But we have quite a nice audience of almost 50 playbacks.
Oh, okay, good.
And I sincerely hope we do not get any copyright issues because of Bugs Bunny and Mickey Mouse.
Well, these are, I guess, yeah, maybe. I did not know. Yeah.
Okay, yeah, so thank you very much. It was great to have you here again. And
thank you again.
We are looking forward to the results of NEMESIS. So, für unsere Zuseher